Organic chemistry. Chemistry is the science that deals with the properties, compositions, and structure of substances. So it studies the transformation they undergo, the energy released or absorbed during different processes. It seems easy when we summarize this significant science into some words, yeah? Never mind. Chemistry branches into 5 primary classes: physical chemistry, organic chemistry, inorganic chemistry, biochemistry, and analytical chemistry. So, what is organic chemistry? Organic chemistry is the study of the structure, properties, compositions, reactions, and preparations of carbon-containing compounds, which include not only hydrocarbons but also compound with any number of other elements, including oxygen, nitrogen, silicon, phosphorus, halogens, sulfur, and hydrogen. Note that most compounds contain at least one carbon-hydrogen bond. This branch of chemistry was originally limited to compounds produced by living organisms, but has been broadened to include human-made substances. Also, it is a highly creative science in which chemists create new molecules and explore their properties of existing compounds. Where can be organic chemistry used? Organic compounds are the central of the economy of today's countries, in rubber, plastics, fuels, pharmaceuticals, cosmetics, detergents, coatings, dyestuff, agrichemical industries, and many more fields. Also, the very foundations of biochemistry, biotechnology, and medicine are based on organic compounds. Organic compounds can be classified into hydrocarbons and non-hydrocarbons, where hydrocarbons are chemical compounds composed exclusively of hydrogen and carbon atoms. Hydrocarbons are naturally occurring compounds and they form the base of crude oil, natural gases, coal, and other important sources. Hydrocarbons, in their turn, can be categorized into saturated hydrocarbons and unsaturated hydrocarbons. The saturated category has one family called the alkanes, and 2 families in the opposite category, alkenes and alkynes. What about non-hydrocarbons? Non-hydrocarbons are carbon-containing compounds which are not only made up of hydrogen and carbon but also of other compounds. Non-hydrocarbons that occur in crude oils and petroleum products may be small in quantity, but some of them have considerable influence on product quality. In many cases, they have noxious or harmful effects and must be removed or converted to less harmful compounds during the refining processes. The most common occurring non-hydrocarbons are sulfur, nitrogen, and oxygen. There may also be small amounts of vanadium, nickel, sodium, and potassium. And the most used example of non-hydrocarbons in our daily life is soup, where each soup molecule has a long hydrocarbon chain. Now, let's head back to talk about the families of each category of the hydrocarbons. Alkanes is an acyclic saturated hydrocarbon. An alkane consists of hydrogen and carbon atoms arranged in a tree structure in which all the carbon-carbon bonds are single. But wait, what does it mean by saturated? They are called saturated because each carbon atom is bonded to as many hydrogen atoms as possible. In other words, the carbon atoms are saturated with hydrogen. The general formula of alkane is CnH2n plus 2. Now into the unsaturated families, alkenes. An alkene is an unsaturated hydrocarbon that contains a carbon-carbon double bond, and it has a general formula CnH2n, with N being 2 or more, which is 2 hydrogens less than the corresponding alkane. Alkyne. An alkyne is an unsaturated hydrocarbon containing at least one carbon-carbon triple bond of general formula CnH2n minus 2. In addition to the other classes, we still have cycloalkanes and alkadene. Cycloalkanes are also saturated, meaning that all of the carbon atoms that make up the ring are single bonded to other atoms, which are similar to the groups of alkanes. Alkadene or diene is a covalent compound that contains 2 double bonds, usually among carbons, and it contains 2 alkenes units. So this schedule here shows the variation in hydrocarbons based on the number of carbon atoms. So it will be either methane, methene, or methane. These hydrocarbons are part of our daily life. Let's see exactly where. Let's start by alkynes. It is used for artificial ripening, and specifically it's based on ethophone or 2-chloroethylphosphonic acid, which penetrates the fruit and decomposes ethylene. Also, it is used in the light portable lamps, which were known as acetylene gas lamps installed in homes, bicycles, and cars. Alkenes. They are used in manufacture of plastics like polyethylene for making buckets, bowls, and bags. Also in the manufacture of acrylic fibers, which are made up of polyacrylonitrile. And finally, into alkanes. Alkanes are important raw materials of the chemical industry and the principal constituent of gasoline and lubricating oils. Natural gases mainly contains methane and ethane and is used for heating and cooking purposes, also for power utilities. Now, what about diving deeper in alkanes? We will talk about the physical and chemical properties of alkanes. Let's start. 1. Structure of alkane. As we have said before, every carbon atom forms 4 sigma bonds with carbon or hydrogen atoms. General configuration of alkane is CnH2n+2. They exhibit tetrahedral geometry with a bond angle of 109.47 degrees between them. Solubility of alkane. Due to very little difference of electronegativity between carbon and hydrogen and covalent nature of CC bond or CH bond, alkanes are generally non-polar molecules. As we generally observe, polar molecules are soluble in polar solvents, whereas non-polar molecules are soluble in non-polar solvents. Hence, alkanes are hydrophobic in nature, that is, alkanes are insoluble in water. They are soluble in organic solvents. 3. Boiling points of alkane. As the intermolecular van der Waals increase with the increase of the molecule size, we observe the boiling point of alkanes increases with the increasing molecular weight. The straight-chain alkanes are observed to have a higher boiling point in comparison to their structural isomers. 4. Melting point. The melting point of alkanes follows the same trend as their boiling point, that is, it increases with an increase in molecular weight. This is attributed to the fact that higher alkanes are solids and it's difficult to overcome intermolecular forces of attraction between them. It is generally observed, like in this figure, that the even-numbered alkanes have higher tend in melting point in comparison to odd-numbered alkanes, as the even-numbered alkanes back wall in the solid phase, forming a well-organized structure which is difficult to break. Now let's swap to the chemical properties of alkanes. Alkanes are the least reactive type of organic compound, but are not absolutely unreactive. 2 important reactions that they undergo are combustion, which is its reaction with O2, and halogenation, which is its reaction with halogens. A combustion reaction is a chemical reaction between a substance and oxygen that proceeds with the evolution of heat and light. When sufficient oxygen is present to support total combustion, then carbon dioxide and water are the products. Alkanes readily undergo combustion reaction when ignited, as this reaction. And the exothermic nature of alkane combustion reactions explain the extensive use of alkanes as fuels. Halogenation of an alkane produces a hydrocarbon derivative in which one or more halogen atoms have been substituted for hydrogen atoms. An example of an alkane halogenation reaction is alkane halogenation is an example of a substitution reaction, a type of reaction that often occurs in organic chemistry. So, after everything we have talked about organic chemistry, don't you get a little curious about who first discovered organic chemistry? Well, 2 German chemists, Justus von Liebig and Friedrich Wöhler. These 2 chemists were responsible for the emergence of organic chemistry in the early 19th century. Their quantitative analytical methods helped establish the constitution of newly isolated and synthesized carbon compounds.